All right, everybody. High Point Physical Science. We are going to go over the chapter review for Chapter 5. And we are going to start on page 107 with number 1. It says, to completely describe a force, including its definition, its standard international units, its symbol, and how it's illustrated in a diagram. So, completely describe a force. Well, let's talk about what we know about a force. We know it's a vector. How do we describe it? It's a push or pull on a system. Okay, the symbol is F with either an arrow above it, or in a book, it's bold print. Okay, and the last thing is, let's draw a force vector, right? We could say this is the force of drag, all right, or the force of whatever you want to label it as. All right, so we draw an arrow. Number 2, list the 4 mechanical contact forces and give an example of each. So number 2, we've got compression. And what's the opposite of compression? Well, the opposite would be torsion. Not torsion, sorry, tension. Tension. Then you have twisting or torsion. And then after that, you have shear. All right, if you can see that. It also says to give an example of each. So I'd like you to try and give an example. My example is hopefully different from yours, but I'm thinking for compression of 2 trains coming together to link, right? So they would be compressing and the link in the middle, and tension would be when one train pulls the other train. Torsion would be if I take a rubber band and I twist it and twist it and twist it, okay, and then I twist it till the rubber band wants to stretch back. I don't have that with me. And shear would be if I take something, say I'm trying to clean dishes, and I put force on the sponge and I'm trying to push on the dishes. All right, so I'm going to have you give your own example. All right, so if you need to pause this right now and do that right now, you can. Number 3, it says, do all the field forces visibly affect all matter? And wow, we really didn't cover this a whole lot. Think of the field forces that you know. So think of gravity. Gravity affects just about everything unless it's close. Some materials are susceptible to certain field forces. What about electric fields and magnetic fields? Not everything is susceptible to electrical and magnetic field. So we're going to write that down. Not everything is susceptible, is to electric and magnetic fields. All right, because some things aren't pulled by electricity, they need to have a charge, right? All right, I think there's a C in there. And everything succumbs to gravity. All right, everything that has mass has some sort of gravity that can pull on it, and it can also pull on another object. Number 4, let's see here. Identify the external forces acting on a dinner plate resting on a table. All right, so we have to draw a picture. And there's our dinner plate. We'll label it. So what's pulling down will be the force of gravity. All right, and what do we call the force of the table pushing up? We call that the normal force. All right, and it's not moving to the left or right because there's no imbalance there. So it says, why does the plate not move? Well, what are we going to say? Those forces are equal. Forces are in equilibrium. So here's a question. You might be saying, well, what's the difference between a larger plate and a smaller plate? The only difference is if the force of gravity gets bigger, well, then the normal force also gets bigger. So the normal force is relative to the force of gravity. Number 5. What is a tendency for matter to continue in its current state of motion, and what quantity is a measure of this tendency? All right, so what is it called? I think you all know the name of it. You call it inertia. And how would you measure inertia? You can't measure it directly, so you measure mass. All right, so you measure it by the mass. Number 6. Use Newton's second law of motion to prove his first law. We did this in the last video, actually. Second law is force equals mass times acceleration. First law, object will, we'll say, let's do the one at rest, will stay at a constant velocity or at rest. If no force is applied. So what does the first law mean? The first law means that acceleration is equal to 0 meters per second squared. The object is not changing its velocity, so it's 0 meters per second squared. So if the force is equal to the mass times 0, the force is also equal to 0 newtons. Well, that looks like it just says the word on, doesn't it? Let's make it this, 0.0 newtons. We'll make it look more mathematical. Number 7. According to Newton's third law of motion, if you exert 20 newtons of force on a lump of bread dough while kneading it, what else must be true? Newton's third law, for every action, there's an opposite but equal reaction. So number 7, the dough exerts 20 newtons back, okay, in the opposite direction. All right, if you're pushing with 20, the dough pushes back with 20. Let's see here. A farmer pulls on his obstinate mule with 250 newtons of force to the right. The ground exerts a reaction force to the mule's resistance of 250 newtons to the left. What is the net force on the mule system, and what is the mule's acceleration? So let's put number 8 up here. All right, we have mule. All right, mule's being pulled to the right with 250 newtons, and the friction is holding him back as he stands still with 250 newtons. What can we say? We're going to say the sum, that's not sum, the sum of the forces equals 0, because this would be a positive, this would be a negative. If you add a positive and negative and they're equal, you're going to get 0. So the mule does not move. He is not going anywhere. All right, number 9. Under what condition of motion is friction between two objects or materials that are touching generally greatest? All right, so let me read this again. It says, under what condition of motion? So it's referring to how the object is moving. So really what it's asking is if it's moving or staying still. So picture that. Is the force of friction greater when an object is moving or when it's staying still? So you really have to think. So what it's asking is it harder to get something to start moving? Okay, in other words, if it's staying still and you want to give it a little push, is it harder to get it to start moving or to keep it moving? So it's harder to get it to start moving. So when it's, the condition of motion is when it's staying still. When it is still, friction is greater. Okay, friction that's applied when something is staying still is called static friction. Static means it's not moving. All right, so when it is still, meaning not moving, friction is greater. Number 10. How does distance between the centers of mass of two objects affect the gravitational force between the objects? So how does distance affect two objects? So closer objects have a greater force of friction. Than far apart objects. You want to be technical, you could say it's inversely proportional. The force of gravity is inverse inverse to the distance squared. So we can be technical if we want. Number 11. Why did Galileo roll balls down a ramp rather than simply dropping them as he investigated inertia? So that's a good question. What happens if you try to measure the time? If I drop something on the ground, okay, and I try to measure how fast it's falling, it's going to be very hard, especially if you don't have a clock, and Galileo didn't have a clock. So it was to slow down the effect of gravity. And measure the rate of falling. It'd be hard enough to do without a clock, let alone if it's going at full speed. Number 12. In order for you to use the distance formula, D equals 1/2 A times delta T squared, what assumption must you make? And how does this assumption apply to free-falling objects? All right. Number 12. Well, have you thought about that? For measuring the distance or calculating it, 1/2 a delta t squared, got my little delta there. The only condition that has to be true is acceleration has to be constant. Okay, if something is speeding up and then slowing down and then speeding up and slowing down, this equation actually won't work. So we have to put down acceleration is constant. Okay, is constant, meaning it's the same, it doesn't change. Constant means, constant in physics means it's the same, it doesn't change. Now, what do we know about G? G is always 9.8 meters per second squared. G is always that number, so it's the same. So that is constant. All right, so that formula works for something that's in free fall. When you apply drag to it, you're starting to change the acceleration and making this less effective, so then it won't work. Number 13, explain the main function of a parachute from a physics point of view. So we have gravity, the force of gravity going down. What do we want to increase? Well, we want to increase the force of drag, right? So we want to increase the force of drag. I'm just going to call it the drag force. And why do we want to do that? Well, so that the terminal velocity meaning the maximum velocity that the person is falling, the terminal velocity, his max velocity or her max velocity is slow. Okay, because if it's too quick, the landing will be painful. So we don't want any painful landing. All right, number 14, it says, physics has explained the why and how of all natural forces. So I'm going to just give you an example here. Think of gravity. Okay, we have explained, okay, the how of gravity. We can describe it, right? Yes, we can describe how gravity works because we said if something's further apart, gravity goes down. If something is heavier, gravity increases, right? So we described it, but what about why? Why is that so? We haven't explained it. Some people are looking for a very, very tiny particle, okay? And they actually call it the God particle in some cases, but they're looking for a tiny particle to try and explain why the force of gravity does exist. But the truth is we have not explained why, so the answer is false. Okay, and so that gravity is just one of the fundamental forces. So how about trying and explain why any of those forces exist, such as the weak nuclear force. In other words, why does a nucleus stay together? Why does it not implode or blow apart? All right, we know what it does and we can describe what it does, but not sure why. Okay, number 15, it says, gravity is the strongest of the 4 fundamental forces. 15, and the answer is false. Gravity is actually the weakest. Okay, it seems very strong because we are on the earth and gravity is definitely very strong towards us, but the size of the Earth is the reason gravity feels big to us. Gravity itself is actually the weakest fundamental force. All right, we're going to stop at number 15. All right, so you're going to earn 15 points just by following along. Sorry, not 15 points. You're going to earn some points by following along on this video and writing down the answers.